Let's take a moment to explore the average value theorem, which is a way to get the average value of a function over an interval. Let's look at this example, which is the function y equals x squared. What I would like to do is get its average value over the interval from 2 to 5. And the first y value is 4. The final y value is 25. But along the way, there's an infinite supply of y values in between. So we won't be able to get an average in the traditional sense because we're faced with an infinite quantity. Instead, what I would encourage you to do is think of this function as a velocity function. And this is the velocity graph. And if we want the average velocity over an interval of time, we would figure out how far the object traveled, and that would be geometrically this area. And then we would divide by the length of time that elapsed, which would be 5 minus 2, or 3 seconds, or whatever units you want to use. So let's see if we can write that mathematically. The average value of this function will be all the area captured from 2 to 5 under the function divided by the length of time that elapsed. And because we know the function, we'll be able to evaluate this expression using the fundamental theorem by getting the antiderivative. There might be times, though, when we don't have the function. We may just have a graph. And if we just have a graph, you could collect this area by counting squares. Also, we may just have data about this function. And if you have just data, you could collect area and evaluate this expression by using Riemann sums. But since we have the function, let's see if we can do it with the fundamental theorem. I'm going to make some room, and let's go ahead and evaluate this. When you integrate the numerator, you get 1/3 x cubed. We're going to put in 5 and 2 and subtract, and then divide by the denominator. And when you evaluate that numerator, you end up with 39, and then we're dividing by 3. So the average value is 13. And this value 13 has a nice geometric interpretation. I'm going to move the graph a little bit further down now, and with a different color, I'm going to mark 13 on the y-axis. And if I were to draw a horizontal line from 2 to 5 at a height of 13, I'll create a rectangle. And the area of that rectangle exactly equals the area of the original blue area underneath the original curve. So basically, this value of 13 creates a horizontal or a constant function that captures the same area. And if you think about motion again, the original curve represents an object that was speeding up over this time interval, and its average value was 13, or its average velocity was 13. And then the red function represents another object moving at a constant speed, capturing that same area, or traveling that same distance over the interval 2 to 5. Let's now look at an example where we're given some data as opposed to a graph or a function. And this is a problem about water in a pond. And we're given, over the course of 15 days, just 6 temperature readings, and there they are. It's worth remembering that this pond has an infinite number of temperatures if we could use incredibly small time increments, but we're given only 6 specific values. And in part B, we're asked for the average temperature of the water over this time interval. So we're going to have to collect all the area under this data and then divide by the length of the interval. Let's go ahead and do that. I'm going to move the problem down to create some space. And to get the average value of this function, we're going to collect all the area from 0 to 15 under the function, and then divide by the length of the interval. And to collect that area, we're going to use trapezoids. I think that was the prescribed method. So our first trapezoid will have a height of 3, and those are its 2 bases, 20 and 31. So the first trapezoid will be 1/2 the sum of the bases times the height. Our next trapezoid would also be 1/2 the sum of the bases times the height. And we would proceed in that fashion all the way until we get to our final trapezoid, which will be 1/2 the sum of its bases times its height. And we would take all those results and add them up and then divide by 15. And I'll leave it to you to do that calculation. But what you should get when you're done is a result that is captured within this span of data. We should get something perhaps in the mid to high 20s, which represents a nice average of all the temperatures in the pond. So that's how you handle data. Let's finish now by just summarizing and generalizing what we've done. The average value of f over any interval a to b is simply all the area from a to b under the function divided by the length of the interval. And I had one student who remembered it this way. It's integral over interval. And you'll often see it written this way, so don't be surprised if it's written with a fraction out in front and then the integral. And the last thing I want to comment on, it's worth noting that your function must be continuous over the interval a to b. If it has holes or asymptotes or jumps, then you won't be able to get the average value.